Please check and let me know if the screen is visible.
Yes, sir.
Yes, sir.
Yeah. So very good morning, all of you. Before we had break, before Diwali, we had completed with the 5 units, and in the last week, we have taken 2 sessions on a revision of few of the topics. We have not yet revised trees, okay, due to the lecture got cancelled on Saturday. Today we'll be starting with our new unit, that is 6th unit, that is graph. This is the last unit from our curriculum. So we are starting with a new unit today, that is graphs. So this is the 6th chapter. As we know, the classification of data structures is in the form of linear data structures and non-linear data structures. And linear data structures we have discussed 2 types in depth, that is stack and queue. And non-linear data structures we have discussed trees as one of the data structure. So graph is another such non-linear data structure which we are going to study. So it comes under the category of non-linear data structure. So graph is a non-linear data structure. And in this non-linear data structure, the elements are organized in random fashion. This we have seen in the first chapter also, that in linear data structure, the elements are organized sequentially or serially, we can say. In non-linear data structure, the first type, that was tree, in that the elements are organized in the hierarchical manner. And the second type, that is graph, in this the data elements are arranged in a random fashion. Okay. So when I say random fashion, we'll take certain examples in order to understand how these elements can be arranged. So I am constructing one graph here in front of you. So suppose this is one node of my graph. Okay, this is another node of my graph. This is another node of my graph. This is another node of my graph. This is another. So here you can see that there are 5 nodes in my graph, and these nodes I am labeling it as, say, we basically call this as nodes or vertexes. Okay, so different textbooks you'll find different terminologies. In some textbook you'll find this as node, and in some textbook you'll find this term as vertex. Okay, so these are 5 vertices, I would say, of my graph. Okay, so I'm labeling these vertices as, say, v1, v2 vertex, v3 vertex, okay, v4 vertex or vertex, and v5 vertex or vertex. So these are my 5 vertices, and these vertices can be connected to each other with help of edges. Now these edges are random. These edges are random. Okay, so I am constructing few edges over here, some random edges. Okay, so I am constructing these edges over here, you can see. So here I am having, say, total these many number of edges. I'm giving some label to these edges. So I'm calling this edge as E1 edge. I'm calling this edge as E2 edge. I'm calling this edge as E3 edge. I'm calling this particular edge as E4 edge. This is my E5 edge, and this is my E6 edge. So total how many edges are there in this particular example? We are having total 6 edges in this example. So what we observe here is graph is basically, if I try to any graph, it basically comprises of 2 major components. The first one is node, or we can call it as vertex, and second one is an edge, and second one is an edge. Okay, so mathematically this graph is basically defined as v comma e. It is defined as v comma e, where this v in the graph G is basically the set of vertices. This is set of vertices. This is set of vertices, and this E in the graph G is basically set of edges. It is basically set of edges. So is the basic definition of graph understood? What is graph? Graph is defined as v comma e, where v is set of vertices and e is set of edges, Now in this particular example which I have quoted here on the left hand side, what is my v? What is my v of g? My v of g in this particular example is set of vertices. So what are my vertices? v1, v2, v3, v4 and v5. These are my 5 vertices. So this is my set of vertices. Okay, and what is edges E of G? What is edges E of G? These are edges. So what are edges in my example? E1, E3, then E4, then E5, and finally E6. So is this mathematical formulation clear to all of you? Yes? Am I audible?
Yes, sir.
Is the basic definition of graph understood? What is graph? Graph is mathematically defined as V comma E, where V is set of vertices, E is set of edges. In the given example, our vertices are V1, V2, V3, V4, V5. Okay, and our edges are E1, E2, E3, E4, E5, and E6. E4, E5, and E6. Okay, now let us see few more basic terminologies related to graph. Let us see basic terminologies related to graph. Now, first terminology that we'll discuss will be adjacent vertices. First will be adjacent vertices. Adjacent vertices. First definition that we'll discuss will be adjacent vertices. So what are these adjacent vertices? Two vertices are said to be adjacent to each other if there is an edge associated between these two vertices. Say for example, if you see in this particular diagram, I can say that V1 and V2 are adjacent vertices to each other. V1 and V2 are adjacent vertices to each other. They are adjacent vertices to each other. Why? Because there is an edge associated between these two vertices. Because there is an edge associated with these two vertices. Right? Two vertices are said to be adjacent to each other. Two vertices are said to be adjacent to each other if there is an edge associated between these two vertices. If there is an edge associated with these two vertices. Now, whether I can call V1 and V3 as adjacent vertices? No, I cannot call V1 and V3 as adjacent vertices because there is no direct associated connecting between V1 and V3. No doubt I have an indirect way to reach till V3, but there is no direct edge associated between V1 and V3, right? So I can say that V1 vertex and V2 are adjacent to each other. These are adjacent to each other. These are adjacent. But if I ask you whether V1 and V3 are adjacent with respect to this example, no, V1 and V3 are not adjacent vertices. Is it clear? Adjacent vertices. The second definition that we'll discuss is path. What is path in graph? Path can be given as the sequence of vertices which are adjacent to each other from one given source vertex to a destination vertex. So if I tell you that I want to go from V1 to V5, suppose I tell you that I want to go from V1 to V5. Okay, so what is path basically? Path is sequence of vertices. So for going from V1 to V5, there can be a path like V1, comma V2, comma V5, right? Comma V2, comma V5 can be a path. This can be termed as a path from V1 to V5. Similarly, V1, V2, V3 is also a path. It is also a path. Similarly, I can say V4, V5, V2 is also a path. Never I am claiming that V1 is always the starting vertex. Right? Never I am claiming that V1 is the starting vertex. Right? It depends upon the problem that we are solving. It depends upon the problem that we are solving. Correct? It depends upon the problem that we are solving. But what is the basic concept of path? Path from a vertex, from any given vertex is sequence of vertices. Now these vertices should be adjacent to each other. I cannot tell that V1, V5, V3 is a path. I cannot tell that V1, comma v5 comma v3 is path. Why I cannot tell this? This is not a path because v1 and v5 are not adjacent vertices. v1 and v5 are not adjacent vertices, right? So in order to build a path, the two vertices should be adjacent to each other. Then only I can connect from one vertex to another vertex, then from that another vertex to next another vertex, and so on. And then I will be able to get a path. Are you getting this? So the above three examples, that is v1, v2, v5 is a path, v1, v2, v3 is a path, v4, v5, v2 is a path, but v1, v5, v3 cannot be called as a path because v1 and v5 are not adjacent vertices. They are not adjacent vertices. Next definition that we will discuss will be cycle. Next definition that we discuss is cycle. What is cycle? Cycle is basically a path in which the first and the last vertex are same. What is cycle? Cycle is a path. Cycle is a path in which the first and the last vertex are same. First and the last vertex are same. So if I tell you that over here v1 comma v2 comma v3 comma v5 comma v4 comma v1, whether it is a path? Yes, it is a path because v1 and v2 are adjacent, v2 and v3 are adjacent, v3 and v5 are also adjacent, v5 and v4 is also adjacent, and finally v4 and v1 is also adjacent. So all are adjacent to each other, right? So we can say, we can claim that this is a path, this is a valid path, right? Now in this particular path, if we observe, the first vertex and last vertex are same, that is v1. So I can call this particular path as a cycle. I can call this particular path as a cycle. I can call this particular path as a cycle. Is it understood? Is the definition of cycle understood? Am I audible, students?
Yes, sir.
Yes, sir.
Yes. Yeah. So let us see now few more new definitions. Next definition that we will discuss is connected graph. Next definition that we discuss is connected graph. See, my dear students, here I am constructing one graph for you people. Okay, so these are my vertices. These are my vertices. Okay, I am constructing few edges over here. Now, my dear students, I am claiming here that my vertex set V is 1, 2, 3, 4, and 5. And I'm claiming my edges to be, suppose if I label these edges as E1, this as E2, this as E3, this as E4. So I'm claiming my edges to be E1, E2, E3, and E4. So if we observe over here, this is a single graph. This entire thing is a single graph. This entire thing is a single graph. But this is an unconnected graph. This is an unconnected graph. Why unconnected? Because there is some disconnection between this part of my graph with this part of my graph, right? So what we understand over here is I can term this as a single graph. I may also call this as two different graphs, okay? But mathematically we all know that graph is V comma E, right? So V is just a set of vertices and E is just set of edges, right? So mathematically I can formulate this as a single graph also. I can formulate this as a single graph also, but here in this case, this graph would be treated as an unconnected graph. This graph would be treated as an unconnected graph. It would be treated as an unconnected graph. Is it understood? It would be treated as an unconnected graph, right? Now what would be connected graph then? Now a graph is called as connected if there exists a path from any vertex to any other vertex of that graph. So from every vertex, if I am able to find a path to every other vertex, then I can say that that graph is connected, as it was happening in my earlier example. From every vertex, I was able to find a path to every other vertex. So from V1, I could go to V2, then V3, then V5, V4 using some path. Maybe there is not a direct edge, but there is some path between V1 to every other vertex. Similarly, from V2 also, I can go to every other vertex of this graph using some path. From V3 also, I can go to every other vertex. Not directly by edge, but by path I can go. We are talking about path over here. Okay. So from V3 I can go to V2, I can go to V1 also by a path. I can go to V5 also, I can go to V4 also, right? Similarly, by V5 also I can go till V4, I can go till V1, I can go to V2, I can go to V3. So from every vertex in this graph, I'm able to go to every other vertex using some path. Then such graph is called as connected graph. So this first example which I had drawn here can be called as a connected graph. This can be called as a connected graph. But this example which I have constructed right now, this is not a connected graph because there is no path existing from 1 till 4 till 5. Correct? Similarly, there is no path from 5 to 3 to 1 and to 2. Are you getting this? Right? So this particular graph is termed as an unconnected graph. It is termed as an unconnected graph. Is it understood? Is the concept of an unconnected understood?
Yes, sir.
Yes.
Yeah. Shall we move
Yes.
ahead with next definition? Okay. So let us see next definition. Next definition is directed graph. Directed graph. Directed graph. Now, if I associate a direction to my edge in the graph, then that particular graph is treated as a directed graph. I'll give you some examples. Suppose I am having this graph over here with 5 vertices, and now I am associating a direction to my edge. See here, for every edge in this graph, I am associating a direction now. In the earlier example, if you see, which we had constructed, here we didn't have any directions to our edge. So this type of graph is called as undirected graph. This type of graph is called as undirected graph. Okay. When the edges in our graph are representing directions, if they are representing directions, then this graph is called as directed graph. Then this graph is called as directed graph. Now this directed graph will have directed paths. Okay. So path in this type of graph will be directed only. Now what is path? As I told you, they are used for going from one vertex to another vertex with help of adjacent vertices. But now here, when I pick adjacent vertices, I should be careful in picking the directions also. So I can say that this 1 3 3 4 and 4 5 is a path. 1 3 is my first edge, I can say, right? 3 4 is my another edge, okay, and 4 5 is my another edge. Here I am writing ordered pairs. Why I am writing ordered pair? Because 1 3 is different and 3 1 is different now. This you might have studied in your discrete mathematics also. Ordered pair, right? So what is ordered pair? 1 3 is different, 3 1. What is this indicating? This is indicating that there is an edge between 1 to 3 in which it is going from 1 to 3. So if it is a directed path, my next edge should begin with 3 only, because 3 was destination of my earlier edge. Then if this next edge is 3 4, which indicates that it goes from 3 till 4, then in my next directed path, my next edge should start with 4, because in the earlier edge the last destination was 4. Then only I can say that this is a directed path. Then only I can say that this is a directed path. Is it understood? Is the concept of directed path understood? Yes.
Yes.
Yeah. So if I am having a undirected graph, I have a liberty. I have a, if I say that my undirected graph, the edge even is representing a flow from V1 to V2 also, and from V2 to V1 also, because there is no restriction of directions in this case. When we are dealing with undirected graph, the same edge even can be used to go from V1 to V2 and V2 to V1 in case of path, right? The edge can be used in both the directions by default. But if we are dealing with a directed graph, the edges are having directions. So 1, 2 is a different edge and 2, 1 will be a different edge, right? In this particular example, we are having edge 1, 2, but we don't have a edge 2, 1 over here. Are you getting this? If I want to have a 2, 1, then I should have another edge over here like this, right? So the same edge cannot be used for both the directions. Every edge will have a independent direction that will be mentioned. It will be having an independent direction that will be mentioned. Is it clear? So the path will be directed. The path will be directed. So 1, 3 edge followed by 3, 4 and followed by 4, 5. So this 3 edges can be called as a directed path in this particular example. Now, if my path is directed, then my cycle will also be directed, right? So here I can give you one example that 1, 3, 3, 4 and 4, 1 is a directed cycle. Again I repeat, 1, 3, 3, 4 and 4, 1 is a directed cycle. 1, 3, 3, 4 and 4, 1 is a directed cycle. See, my dear student, it is never claimed that a cycle should include all the vertices. No, don't go in that wrong understanding. It is not told that cycle should include all the vertices. No, cycles can be small cycles also. So here in this example, if you see 1, 3 is a edge, directed edge from 1 to 3. The next edge is 3, 4. So wherever my first edge is ending on 3, there my next edge is starting, that is 3, 4. After that, I'm having another edge that is 4, 1. So my earlier edge was ending on 4. My next new edge is starting from 4 and it is going till 1. Now this directed path, which is from 1 to 3, 3 to 4 and 4 to 1, this particular directed path is having vertex, source and vertex destination as same, that is 1 and 1, right? So this directed path where my source and vertex are same can be termed as directed cycle. It can be termed as directed cycle. Is the example understood, my dear students? Yes. Is this example understood?
Yes.
Yes, all of you understood this example?
Yes, sir.
Yeah. Yes, sir. So if we are dealing with undirected graph, our edges will be undirected. They can be used to go from both the ways, right? The path would be also undirected in that case, and cycle would also be undirected in that case. But if we are dealing with directed graph, then every edge will have a direction associated. So that edge can be used to traverse from the with the help of that direction only. So the source and destination will be fixed. And in such graphs, the paths will be directed paths and the cycles would be directed cycles. Cycles would be directed cycles. Okay. Now let us see few more definitions. Next definition that we'll discuss is degree of graph. Next definition that we'll discuss will be degree of graph. Degree of graph. Now when we are dealing with degree of graph, we have seen degree of tree, if you remember, right? So similar concept is there for graph also. So what is degree of graph? It is basically the number of edges associated with that particular vertex. So when I'm calculating degree of graph, basically I'm calculating degree of vertices, not a degree of graph basically. So I should not write degree of graph. These are degree of the vertices in that graph. Degree of vertex in that particular graph. So if I ask you what is degree of 1, example, degree, because these two edges. So degree of V1 is 2. What is degree of V2? Can anyone tell me what is degree of V2?
3.
3. Absolutely correct, because there are 3 edges associated with V2. What is degree of V3?
2.
2. Correct. What is degree of V5?
3.
3. Absolutely correct. And what is degree of V4?
2.
2. Correct. So degree of any vertex is the number of edges associated with that particular vertex. Okay. Now if suppose I tell you that degree of a particular node is 0, what it indicates? If I tell you that there is another vertex V6, and if I tell you that this V6 also is also part of this graph, if I tell you that this vertex V6 is also part of this graph, it can happen, right? So now this will no longer be a connected graph. This has become an unconnected graph, right? What will be degree of V6? Yes. What will be degree of V6?
0.
Correct.
0.
Degree of V6 will be 0. So if for any vertex in a given graph, if the degree is found out to be 0, what it indicates? It indicates that this vertex is an isolated vertex. Okay. If the degree is 0, what it indicates? It is not connected to anyone, right? If its degree is 0, then it is not connected to anyone, right? In case of an undirected graph over here at least, right? So we can claim that this is an isolated vertex. Is the concept of isolated vertex understood? Yes. If the degree of that particular vertex is coming out to be 0, so there is no any edge associated with that particular vertex. So we can term that particular vertex as an isolated vertex. We can term that particular vertex as an isolated vertex. Now this is about the undirected graph. When we are talking about degree, this is for undirected graph. If we are dealing with a directed graph, coming back to this example of directed graph, let us discuss how the degree works. Let us discuss how this particular degree works. Now, when we are dealing with a directed graph, the degree is basically divided into two parts, in degree and out degree. It is divided clearly the outgoing edges of that particular vertex. So if I am talking about vertex 1, if I am talking about vertex 1, what is in degree for vertex 1? Can anyone tell me? What is in degree for vertex 1? Yes, anyone?
1.
No.
2.
Anyone else? 2.
2.
Yes, you can see there are 2 incoming edges to 1. Which are the 2 incoming edges? This edge which is going from 4 to 1, and this is another edge which is coming from 2 to 1. So in degree for vertex V1, if I am talking about vertex V1, if I am talking about vertex, what is in degree 2? What is out degree for vertex V1? How many edges are outgoing from 1? 2 edges, 1 2 and 1 3. So out degree is also 2 for vertex V1. So what will be my total degree? My total degree of vertex V1 would be addition of in degree and out degree, which is coming out to be 4. Which is coming out to be 4. If I take more example, suppose I am taking another vertex this part, so some space will be created. Okay. So if I am taking another vertex, suppose V2, for V2, how many incoming edges are there? There are 2 incoming edges, 1 2 and 4 2. So in degree is 2. And how many outgoing edges are there? Again 2, that is 2 5 and 2 1. So out degree is 2. So total degree of vertex V2 is 4. Let us take one more example. Suppose I am taking vertex V5. Suppose I am taking vertex V5. Do we have roll number 55? Roll number 55?
Yes, sir.
Yeah. What is in degree of vertex V5? Is my question clear? Are you able to hear me? Roll number 55. Roll number 55. Stay alert during the lectures. Do we have roll number 18? Roll number 18?
Yes, sir.
Yeah, what is in degree for vertex V5?
Sir, 2.
Correct, 2, because there are two incoming edges. What is out degree for V5?
1.
1. So what will be my total degree?
3.
It will be 3. Absolutely correct. If I take one more example, suppose V3 is my next vertex. Do we have roll number 12? Roll number 12?
Yes, sir.
Yeah, what is in degree for vertex V3?
2.
It is 2, correct. What is out degree?
1.
1. So what will be total degree for vertex V3? It will be 2 plus 1, that
3.
is 3. And finally, if I tell the last vertex, that is V4 vertex, do we have roll number 49? Roll number 49 is there?
Yes, sir.
Yeah, what is in degree for vertex V4?
1.
Very good, 1. And what is out degree for vertex V4?
3.
Very good, 3. So the total degree for V4 will be
4.
1 plus 3, that is 4. Correct. So I hope all of you have understood now the concept of degree when it comes to directed graph and undirected graph. So in case of undirected graph, we don't have any directions associated, right? So it is only about the edges. There is no in degree, out degree concept over here, right? But in case of a directed graph, we have two components, in degree and out degree, and addition of these two will give you the final degree for that particular node. Give you the final degree for that particular node. Is it clear? Now, next definition that we'll discuss is complete graph. Next definition that we'll discuss is complete graph. Now, a graph is said to be complete, or we can say it is also called as fully connected graph. There is another terminology used for the concept. A graph is said to be complete, or it is said to be fully connected if there is a path from every vertex to every other vertex of that graph. I'll write the definition so it will be more clear for you. A graph is said to be complete, or we can say fully connected if there is a path from every vertex to every other vertex of the graph. Sorry, not path, edge. A graph is said to be complete or fully connected if there is an edge from every vertex to every other vertex of graph. Means all the vertices are connected to each other with help of corresponding edges. Then in such situation, we call that particular graph as a complete graph or fully connected graph. Complete graph or fully connected graph. Is it understood? Yes.
Yes, sir. Yes, sir.
Is the concept of fully connected graph understood?
Yes, sir.
Now we have one more, that is weighted graph. This is the most important graph which you are going to carry forward in the next year also. I told you that there is one more subject, that is computer algorithm, which you are going to study in third year. So many problems will be based on weighted graph. What is weighted graph? A graph is said to be weighted graph if every edge in that graph is assigned some weight value. Okay, first I'll write the definition and then I'll give you the example. A graph is said to be weighted graph if every edge in the graph is assigned some weight value, This weight value would be the numeric weight values that we assign most of the times. So I'll give you some example. Suppose I am having a graph like this, vertex v1, v2, v3, and these are the edges associated with this graph. Suppose this is an undirected graph. Okay, I am writing some weight values 20, 24, and 30. So these are some numeric metrics to connect between these connecting graphs. This basically are used to solve some problems. For example, these numeric values can be distance. So I can keep my cities as vertices, and these edges will be nothing but the roads, and the numeric values are nothing but the distance. So if I want to solve a problem to find the smallest distance from any given city to any other given city, we all use Google Map, right? We all use Google Map. So Google Map is what? It is basically application of graph in which you have all those cities represented, all those positions represented in the form of vertices, right? And the edges are nothing but the roads, and these numeric values are nothing but the distance. These are nothing but the distance. So this Google Map application is basically using weighted graphs at the background. The data structure used for that is weighted graph. Is the application understood where this weighted graph is used and the example of weighted graph? Yes. Am I audible? Am I audible, students?
Yes, sir.
Yes.
Is my voice breaking? Is it clear today? Yes.
Sir.
Is or do you have any disturbance?
No.
It is clear, na? Okay. Let us see one more definition. That is tree. Now we have already studied tree. Entire chapter we have studied for tree. But now here we are defining tree in terms of graph. Here we are defining tree in terms of graph. Now what do I mean by that? If you remember, if I give you some example of a tree, suppose this is a tree. Correct. This is one tree which I have constructed. Whether this is a, can I call this tree as a graph? Yes. Can I call this tree as a graph?
Yes, sir.
Yes, I can call this tree as a graph because this is nothing but vertices and edges and they are connected. So indirectly what we can comment is all trees are graph. See, all trees are graph. All trees can be treated as graph. But whether all graphs are trees? No. Whether I can call this graph as tree? No, I cannot call this graph as tree because tree has to be in the level format. And I cannot connect two vertices in the same level, and there cannot be a cycle also. Here you can see there is a cycle. When I taught you tree, I told you that in tree there is no cycle, and there is a format in which the vertex can be connected to each other. In the leveled format only it is, right? So what we can comment over here is All trees are graph. All trees are graph, but all graphs are not tree. But all graphs are not tree. Is the statement understood? Right? All graphs are. So can I define tree in the form of a graph? Yes. How I can define that? Let us define it. I'm defining now tree as a part of graph. Now a graph is a tree if it has following properties. If it has following properties. First one, it is connected. We all know that graph can be connected and it can be unconnected or unconnected also. Now when I have unconnected component, then I will not get a single tree. I will get forest in that case, right? So for getting a single tree, my basic requirement is that it should be a graph. My basic requirement is that it should be a graph. Correct? My basic requirement is that it should be a graph. Yes, it is understood. And it has to be connected. And it has to be connected. Second, there are no cycles in this graph. There are no cycles in this graph. There are no cycles in this graph. So a graph is a tree if it has following properties. First one, it is connected. First one, it is connected. Second, there are no cycles in that particular graph. Then I can call that particular graph as a tree. Then I can call that particular graph as a tree. Okay. So to just quickly revise what we have seen today. Today we have started with our sixth chapter, that is graph. And we have seen some basic terminologies related to graph. What are those? First one, we have seen definition of graph. Graph G is V, E, where V is set of vertices, E is set of edges. Second, we have seen what is adjacent vertices, what is path, what is cycle, right? After that, we have discussed about connected graph and unconnected graph. Then we have seen directed graph. In directed graph, we have a directed path and directed cycle. Then we have seen degree of graph for undirected graph and for directed graph also. So for directed graph, we have in degree and out degree before we find the final degree for directed graph. And then we have seen complete graph and weighted graph. Complete graph and weighted graph. You may get few definitions in your theory paper on graph. So you have to give relevant examples, or you might get a short note like write basic terminologies of graph. So you need to write definitions and you need to give these examples. Like we had a short note questions in tree also. Explain basic trees. You can have a theory. Explain basic. Where you should define what is graph. You should give one example. You should talk about adjacent vertices, path, cycle, degree, connected graph, weighted graph, and degree in directed and undirected graph both. Is it clear? Yes, students?
Yes, sir.
Yeah, with this,
Yes.
we will stop for today's lecture. Let me download the attendance. Just hold on for a moment.